But I didn't get any email questions. How many understand how to add capacitors and inductors? I'm just looking. Do you have a question? If not, I'm going to move on. Because that is straightforward. However, make sure you know how to do it. Yes, miss. Yeah, you're going to have, we're covering some stuff today on transient analysis that you'll be doing. So I want to make sure that everybody understands the fundamentals about capacitance and inductors. You all with me? All right, now the next thing we're going to do is go ahead and actually talk about transient phenomena, time-varying phenomena on capacitors first, all right? Now please, this is review. Everybody had this in physics, but I'm going to show you sort of a methodical step-by-step method that will try to alleviate a lot of the what do I do next problem. So when we have a capacitor, this is the symbol for capacitor. The units are in farads. There's going to flow a current right here, I of t, right there, and that I of t, there'll be a voltage across here, I'll call it Vc of t. I of t is given as C dV dt. So it's the time derivative of the voltage across the capacitor multiplied by the capacitance that tells you what the value of the current is flowing through it. You'll notice the arrow direction. The voltage is sensed plus the is really plus the minus, and that's anybody. You can put the plus down here if you want. But where the plus terminal is, that is the direction the current's flowing. Can everybody see this? In the back, can you guys see it? Okay. And if you can't, let me know. Now, the next thing we do is the simplest possible circuit. And if you took probably your, I'm not actually sure about this. Has anybody taken the GREs, what I'm about to say? Anybody? You probably will. I think it may have been on ACTs, but I'm not sure. Fundamental RC or RL behavior is usually something you get in high school physics, and they ask a question or two about it, I think on the SAT and ACT, unless they change it. And it's based on this. If you have a capacitor, as such, and then you have a resistor here, as such, and I make this statement, I'm going to say at t equals 0, there's going to be some voltage across this capacitor. I'm going to call it Vc of t. I'm going to say Vc at t equals 0 is some V naught. Now, does everybody follow me? I'm just saying there's going to be a voltage, a known voltage at t equals 0. I don't care how it got there. Everybody with me? Now, when you look at this, I know that known voltage is going to cause a current to flow, I of t, and that I of t would be equal to C dV, and you can call Vc of t. I'm just going to put the Vc of dt here. Everybody follow? Now, after that, the only thing I'm going to do is say that current flows this way, so it's flowing literally this way. I'm just showing you the direction. It's, if positive current enters the positive terminal, this is the definition of the direction of current. Now, how many see that and clearly understand it? You with me? All right. Now, how do you want to solve this? This is the one unique case where R and C are both in parallel in series. They have the same voltage, and they're connected in series, the same current. You all see that? It's with two elements. If they're connected together, that's the only possibility. So I'm going to start here. I'm going to go around the circuit and sum the voltages. So here, I get Vc of t. I'm going to drop that in a second. Then if you take a look at this, the actual voltage here is minus the plus. Do you all see that, class? I want you to see it. Notice the direction of current, right? How many see that the actual voltage would have a plus on the bottom of the resistor and a minus on the top based on the direction of current flow? Can you all see that or not? Whenever I see this, I get nervous. Can you read my writing? Let's try that. Okay. All right, now when I come here, I get an increase, and what happens here? Increase, right? Negative to positive increase. How many see that? And it would be an increase. What would it be? It would be R times I. Do you all see that, class? How many do? Y'all follow me on this or not? I'm very concerned whenever I don't see, when I'm not sure, when I get that look of, huh? That concerns me. It's current times resistance is voltage, right? So it's going to be really plus I of t times R, and that has to sum to 0. I just went all the way around to where that x is. Everybody see it? Now, I'm not going to ask you to write these differential equations, so don't go there. You're not going to be solving differential equations. I'll show you the standard form of the solutions, and you'll get it. By the way, I might as well say this first off. Whenever you see a capacitor in the circuit, regardless of what they care about, they want a current somewhere, the only thing you worry about initially is the voltage across the capacitor for all time. You all hear that? Only the voltage across the capacitor. Everything else is based on that. So with that in mind, now I put down Vc of t plus R, and then I is C dV dt, right? I really don't need to keep putting Vc of t. It is a function of time. It's implied. Everybody with me? That's a first order differential equation. This is something engineers, whether they despise differential equations or not, this is something that most engineering is based off of, this and higher level differential equations. Take a look at this. All right, let's go ahead and just solve this one time. How do you solve equations like that? Well, how many know you could use Laplace transforms? It's like, I've never heard of it. Yeah, you have. I mean, in mathematics, you've had it. How many have had Laplace transforms? I'm not going to require you to know, but at least I want some honesty. Yeah, you've had it. So what I'm going to do is, I'm going to do just a simple method of integration. You don't even need an integration factor. So I take this, actually I'm going to first divide by RC, and I'm doing this to make my life easy, and I hope you all see this, right? Now when I divide by RC, that's constant. Do you agree with that? Whatever the R is, whatever C is. Take that term to the other, or actually leave VC dt here, take that to the other side. You might not have done this in a while, but yes, sir?
Can you explain again how, if it's going into the positive terminal of the resistor and out the negative, is that not a drop?
All right, how did I sum voltages? This way, right? Isn't that a voltage increase VC? Can you see that?
Okay.
I'm going the other, I'm not going counterclockwise, I'm going clockwise. Do you see it now? All right, now at this point, yeah, you can do Laplace transforms, you know. So what I'm going to do is first multiply both sides by RC. Well, actually, I'll leave RC on this side, so I'm going to take 1 over RC here. And then I'm going to multiply by dt. Now, if you want me to break it down to steps, I will, but this is pretty straightforward. Multiply both sides by dt. And then I'm going to divide by VC. That's the variable. You all with me, class? When I do this, I get this. Now, does everybody see this? Can you read it in the back? This looks very familiar. So I have a form of it. I'm going to now integrate. It's going to be an indefinite integral, as such. And let me just show you the form. What happens when I have dx over x? What does that go to? Anyone? Mechanical. Industrial. Civil. Anybody? Natural log, yeah. All right, so here I get the natural log of VC is equal to minus T over RC, and technically you should put a constant. And I'm going to call that constant K. Doesn't matter what the symbol is. Remember, an indefinite integral, you always have to add a constant. Do you remember this class? If it had hard limits, then you wouldn't, but it doesn't have hard limits. So next, after that, I need to solve for VC of t. So what I'm going to do is take e to that entire equation. When I take e to the log of VC, it just becomes VC. Do you all agree with that, class? Everybody follow me on this? So I get, and I'll write it here, VC, and this is time I'll put the t in here, And that's going to be equal to what? EXT, an exponential here, and it's going to be to the minus T over RC, and it's plus K. Now, at this point, catch up with your notes, and we're going to erase everything under that equation, so I'm going to finish it. I know this is rudimentary to some of you, but I need to at least show you, give you some background for why it works. So it's based on the mathematics. Now erase all this. And when I look at that, I find out I get an equation. Now remember, I'm just showing you the basic equation. Now you're going to get VC of t equal to e to the minus t over RC, but it's times also e to a constant minus k. Now I'm going to make the claim, if k is an arbitrary constant that we don't know, e to the minus k is another arbitrary constant. You give me that one? It's a constant. Well, I don't know what it is. I don't care. But this is the form. So I'm going to use the symbol, I'm going to use k again. That's the form of the voltage on a capacitor if there are no voltage sources in the circuit. You all see this? The only thing that's going to be assumed is at t equals 0, there'll be some voltage. You all follow me? How that voltage got there doesn't matter. Now, how to find K? Well, that's the initial conditions, right? Initial conditions. We said at t equals 0, we have V naught. You all follow me? Give me a show of hands. I gotta make sure you hear me and understand. So I just simply put V naught over here. I put VC t equals 0 is equal to V naught. And that's equal to K times e to the minus 0, isn't it? Do you agree with that? What is e to the minus 0 or e to the plus 0? Right? So now I have the value of K. K is simply equal to V naught. Or I can say VC of t is equal to V naught, the initial voltage at t equals 0, e to the minus t over RC. And I'm going to state one other thing. Usually instead of writing RC over and over again, they introduce the symbol tau. It's a time constant. And it's equal to R times C. And the units are seconds. Y'all with me, class? How many remember that from physics? Probably one of the simplest things that you had to deal with. Now, the next thing we're going to do is talk about a slightly more complicated circuit and the way you go about doing it. As a matter of fact, I'll put the steps down one by one. And this is when there is a source, either a current source or a voltage source in the circuit you're analyzing. There'll be switches too, and I'll explain that. I didn't look at the weather, but is it supposed to rain all day? Yes? Well, there goes Kenneth. I'll survive. All right. So the next thing I'm going to go right to the more complicated problem, but this, I'll lay this out step by step. So where is this? I'll tell you what. I'll take a step back. I'm going to do a slightly less complicated problem, but I'm going to lay out the steps. So this is the classic kind of problem you're going to get. What I'm about to show you, all the problems that you will get related to capacitors and resistors are going to be based in large part on what I'm showing you now. They'll have different circuit configurations, but the fundamental steps will be the same, and I'm going to show you the trick. So in this one, I'm going to draw this, and I'm going to put a battery here. I'm gonna say this has got plus or minus, I'm just gonna call it some Vs. That would be a value like 10 volts, 20 volts, 30 volts. Y'all follow me? Now, you're gonna have some resistance, or you're gonna have a switch next. The symbol for a switch, something that can change states from an open circuit to a closed circuit, is this. And then you're gonna have a resistor R and a capacitor C. And again, this capacitor will have a value C. What you're always after, and the only thing I'm after at this point, is the voltage across the capacitor as a function of time. That's what we're after. Now, for this problem, I'm going to assume that the voltage across the capacitor, this switch changes states at t equals 0. By the way, this is like the third, I've complained twice, sent emails, and thank you for sending a message about this light, but it's still not fixed. So after class, somebody remind me to walk down the hall and talk to these people. One of them's John Tennant, the other, well, there's a few people I need to talk to. And I'm going to personally bring a ladder up here, and either they're going to change this or I'll shoot it out, one of the two. We're going to take care of this problem because it's, I mean, this thing's been going on since the beginning, right? This is unacceptable to me. All right, back to this thing. Now that's a VC of t, this is a VS. I hope you can read it in the back. Now, hear me on this is important. I'm going to say for t less than or equal to 0, the voltage across that capacitor is 0. So I'm not assuming that there's an initial voltage. I don't want to complicate it. Y'all with me? Now, we talk about what a capacitor appears to be when there's a transient phenomenon. And this is important. So if you look at a capacitor here, and I said if there's a voltage across that capacitor, there will be a current I of t through that capacitor that is equal to C dV dt. Can everybody follow me in that? I mean, just a show of hands. You don't have to yell and scream. With me? Now, this is important. Whenever there is a, like if you had this capacitor as such, let me try to draw it for you. If you had a resistor here, and say you had a switch here, I'm not gonna spend too much time. I gotta give you some perspective. Call it t equals 0. And put a battery here with 5 volts. And then you got a capacitor here with no charge on it initially. And I look at VC of t here. Now, hear me. Initially, when you throw that switch, that capacitor looks like a short circuit. You all follow me? There's going to be an instantaneous change in the voltage from some value to some other, tries to be, all right? But current can't go to infinity because it's limited by R. Do you all follow me? R, I mean, the most current you could get is 5 over R. Do you agree with that, class? Now, what that means is, initially, this looks like a short circuit, just as the switch closes. There's no voltage. But as time goes on, and this thing goes to a stable state where there's less and less change, in other words, it's charging, at the end of the day, as t goes to infinity, it looks like an open circuit. Do you all follow me? So if I looked at this circuit, and I wanted to know the value of VC of t as t goes to infinity, what would it be? Think about it. Do you all agree the voltage would be a constant on every element of the circuit as t goes to infinity? How many see that? It has to be. There's no other possibility. It's not a second order differential equation. It has to go to a steady state. Do you all follow me, class? Now, in that case, I know that no current would flow at t equal infinity. Do you agree with that? If no current flows, how much voltage is across that resistor? Anybody? 0. Do you all see that? How many do? No current, no voltage, no problem. If there's no current flowing in here, this voltage has to be 5 volts. You all with me, class? That's at t equal to infinity if that switch closes at t equals 0. Now that's one of the key things. The voltage, just as the switch goes from 0 to 0 plus, is 0 across the capacitor, because, and this is the other thing, voltage can't change instantaneously across the capacitor. It's a continuous change. You all follow me? It can't have a discontinuity. That would imply an infinite current. That's not a possibility. You all with me? How many see this and understand? Trying to give you perspective, I'm trying to make it simple. Do you guys see it right there or not? I mean, maybe you're bored, but I want to make sure. Do you all see it? All right. No?
I'm a little confused.
Ask the question.
Why is, so you're saying when it closes at t equals 0?
You see, from t equals 0, all of a sudden, there's no source in the circuit to a source in the circuit, right?
Sure.
Instantly, when that closes, this will look like a short circuit, guaranteed. The current through here would just be, at t equals 0 plus, would be 5 over R. All right, that's it. And what that is that current is really the rate of charge transfer. So it starts adding charge on these plates. Initially, there's no charge, and it's at a gradual rate, and it will all of a sudden charge up, exponentially charge to a constant value at t equal infinity, and that value will be 5 volts. Now I'm just trying to give you perspective on this. Do you all see it? Back to this problem. When I look at this, I'm after that voltage VC of t. Now I can write the differential equation just like I did last time and solve it. This is going to have, it's a homogeneous equation, but it's not set equal to 0. So that means there's going to be a constant in the solution. I'm going to put this down so I don't waste a lot of class time on some basic math, but I'm going to put this down here. I'm going to show you something. I want to come over here and give you some perspective on why we're doing what we're doing. So, when you look at this, if there is a voltage or current source in the circuit after the switch closes, y'all follow me? If there's not one there, it's a different problem. If there's no source, if somehow this got taken out at t equals 0, then the voltage will always go to 0 on the capacitor. Got me on that, class? It'll always go to 0. There's nothing to keep the charge there. It'll go to 0. There'll be no energy in the system as t goes to infinity. But the way it is in general for all transient first order problems, your VC, write this down, of t, the voltage across the capacitor, is going to be some value K1. K1 is just an arbitrary constant. I'll show you how to get it. Plus a second constant. And it will be times e to the minus t. And then the R here will be the Thevenin equivalent resistance across that capacitor. I'm going to get to that. So it's R Thevenin times C. This equation you box. Anytime you're worried about the voltage across the capacitor for a transient problem, some of the MEs, and I'm sure other engineers in here, will be using RC circuits for timing. Has anybody done that in here? You have, ME? All right, you'll be doing things like that. They're great timers. There's other tricks I can show you, but this is a standard timing circuit. So, or it's one portion of a timing circuit. There's also a recharge thing. When I look at this, K1, write this down. This is the voltage across the capacitor as t goes to infinity. Now, let me explain why. As t goes to infinity, do you see how e to the minus infinity is 0? How many do? That means the second term, K2 e to the minus t over R Thevenin times C, it goes away. So K1 is just the voltage across the capacitor t equal infinity. And I'll show you how to get it in a second. You with me? Now, the next thing is, and I'm going to put this down here, R Thevenin, this is the thing you need. That is the Thevenin equivalent resistance across really sense. So if I rip that capacitance out, and I look for the Thevenin equivalent resistance across there in the state that I'm interested in for t greater than 0, I'll show you how to get that too. You with me? All right. That's our Thevenin. You need this, you need this. Then after you have that, you get really the time constant tau, which is R Thevenin times C. Now C is known, so that is, once you get our Thevenin, the time constant is a gimme. You all follow me, class? It's known. And then, when you look at this, VC at t equals 0 plus, this is just after the switch changes state. Got me? It was open, now it closes. That would be the value of K1 plus K2. Now you can see that because when the switch closes at T0 plus, you have e to the minus 0, which is 1, right? So initially, before the switch closed, the source doesn't have a chance to influence the values. But when it closes, it does. Do y'all follow me? Give me a show of hands if you understand what I'm saying so far. This is physics. You guys back there got this? I mean, I've got to make sure. In the far back, you guys okay with? Don't worry if you want to chit chat. Keep it low. I don't care. I just want to make sure you see this. With me? Now you've had this kind of stuff. I don't think the mythology I'm showing you. Did you have Thevenin in physics? I didn't think so. I mean, maybe you get a good teacher, he might show you this trick, but we're going to go through this because once you have this right here, you have the voltage across the capacitor. Do you agree with that? If we have K1 and K2 and our Thevenin, we have the voltage across the capacitor for all time t greater than 0. Everybody agree with that? Now, if we have that, do we have the current here? What is the current? Anybody remember? C times dV dt, right? That's one way to get it. Just take a time derivative of the voltage. Another way is, well, now I have this voltage as a function of time. Now listen. When the switch closes, I have a battery here, right? So the voltage Vs minus the voltage Vc of t, you might as well put a ground here to make life easy, is developed across this resistor. That current would be Vs minus Vc of t over R. How many see that? Just listen to me. This is Vs with respect to ground. This would be on this terminal when the switch is closed. I'll make it easy for you to see. You agree with that? That's for t greater than 0. Agreed? That voltage is on this side. I want the current this way, I of t. The voltage on this side with respect to ground would be Vc of t. Now I know that. I'm assuming I can get that. You with me? So Vs minus Vc of t divided by R would be the current. Do you all agree with that? Show of hands if you do. I want to make sure I'm talking to people and they're getting it. You with me? All right, now, I'm going to go back to that problem. That's the steps you go through. Now I'm going to show you how to get each of these values for this particular problem. So I'm putting the switch back in. And now we're going to go ahead and get these values. All right. The very first thing I'm going to do is this. I'm going to say that I'm assuming the voltage across the capacitor for t less than 0 is 0. It doesn't have to be. You all with me? I could have an initial voltage. It doesn't matter. Now, if that's the case, once the switch closes, you know the voltage across the capacitor for t equals 0 plus, that's just after it closes, is 0 also. It can't change instantaneously. You all with me? There can't be a discontinuous change in voltage across the capacitor. It would imply an infinite current, because C dV dt would go to infinity. Everybody with me? Now, the next thing I do, and this is the way I do it, and I'm going to try to make it real obvious. We're looking at t greater than 0. So for t greater than 0, take out the switch and do this. I know it's in a charging mode. That capacitor at that point is charging up, right? How many see that? What is it going to charge to as t goes to infinity? It's going to charge this voltage, and that's what I call K1. You all see that? You can use any symbol for that. How many see that right there? All right, over here. You guys got it? So that means now I have K1 here. And I put it down. K1 is equal to Vs. All right? Now I need to get R Thevenin. This is important. With R Thevenin, how many remember R Thevenin? Thevenin equivalent. What did you do if you wanted the Thevenin equivalent value of resistance after you ripped an element out? I'm about to rip the element out with the capacitor. And I want the actual Thevenin equivalent resistance between these two terminals. Well, what did you do? You turned off the sources. How many remember that? If it was a current source, it became a open circuit or just cut it out. If it is a voltage source, it becomes a short circuit, a wire, however you like to think about it. So let's get rid of it then. Make life easy. What's the value of R Thevenin for this circuit? How many say it's R? I mean, I don't think you can go wrong here. With one resistor, it's got to be this. So R Thevenin is R for this case. We're going to do a slightly more complicated one next. It's the only way I can get you to see this. At least I feel comfortable doing it. How is R Thevenin times C? You don't have to go through that calculation. I just put it there because remember the time constant is not C or R Thevenin. It's the product of the two. You all with me? That's the only reason I write it down. Finally, I got the value as t goes to infinity, but I know the value as t just as it turns on is 0, right? Now listen to me. I'm going to write the equation right here. I know that the general form there, Vc of t, is equal to, I got K1, right? That's Vs. Does everybody see that? I'm going to put it in. Plus, I'm looking for K2. K2 times e to the minus t over tau. I'm just putting tau there because I don't feel like writing R Thevenin times C. Now, at t equals 0 plus, it's 0, right? What did I say this term becomes, class? 1, right? It has to, it's 0. What is K2 in this case? Minus Vs. Minus Vs. Do you all see that? You don't? How many see it? All right, sure. This is going to be K2 is equal to minus Vs. Now, what does the equation look like? Well, for that particular problem that I erased most of it, Vc of t is equal to K1 Vs, right? And then if I factor that out, it would be 1 minus e to the minus t over tau, isn't it? How many see that? I'm just factoring out Vs because it appears twice. Everybody? Now, that's a simple way to think about this problem, but I laid out the steps right there. Find voltage as t equal infinity. Voltage just after the switch transitions at t equals 0. And I'm not going to try to trick you to make the switch transition at 1 second. It'll always be at 0. You all with me? Then you have to find R Thevenin. Did I put the whole thing together? So let's do a little more complicated problem with those steps. I think you'll see. You with me on this one? I hope. Are you? All right. I see a bunch of police coming in here. I'm going to be concerned. By the way, has anybody been in one of these buildings when there's a fire alarm? Anybody? Fire alarm? You have? Let me tell you what happens. You have to evacuate first. And if it's raining outside, it's not fun, but you got to get out.
Second of all, you can't get back in until the fire department clears the building to make sure there's not something burning or things like this. And the best time for that to happen is during an exam. It usually does. And it usually is somebody that didn't want to take that exam. Now that's a joke, but there have been fire alarms pulled and nobody to blame for it, mysteriously, and I've always suspected that. Always when there's a big exam. Don't do it. Did they do that in your high schools? I mean, fire alarms are the most irritating thing. All right, this is actually figure 410 in the book. Write that down, figure 410. All right. This is a 6-volt DC source, time invariant. I don't know. 1K, I'll make it 1K. And C is 200 microfarads. And here's what the problem is going to ask. They're looking for the current here as a function of time through that resistor. Do you all follow me? We're going to go through it, but I want to make sure you can see this. Before you just jump into these things, remember what I told you. You're after the voltage across that capacitor as a function of time. If you can find that, everything else falls apart. How many can see if I can get the voltage across that capacitor? I'm going to label it here, Vc of t. For t greater than 0, then I can simply divide that by R2 to find that current. How many can see that? Can you see it, or can you read my writing better? You good with it? Far back. You guys okay with it? All right. So we're going to go ahead and apply the same method that I've talked about to do it for this one. You all with me? Now look at this though. At t less than 0, this is shorted. Do you all see this, class? I'm going to need that part of the board, so I'm going to erase this over there. Does everybody have these steps down? I want to make sure you see this. And if somebody ever finds the eraser that was here, please let me have it. Oh well. Eraser's coming up. I'm going to do a little redraw here too. You can do this at the beginning to help see things. When I look at this right here, for t less than 0, this circuit actually looks like this. It looks like I have a voltage source, 6 volts. That's a short circuit, so I have a resistance R1. I'm just going to call it R1. Then I have that place where the capacitor is. I'm going to show you something. And then I have a second resistor, R2. Now I want you to just first convince yourself that's exactly the representation for t less than 0. How many see that? All right. At t less than or equal to 0, there is no change in the actual voltage in the circuit. It's a DC voltage. It's been there since time began. What it means is the capacitor can be replaced by an open circuit at that point. You can erase that and just say this is an open circuit. But what I need is this voltage, Vc for t less than 0. Can everybody follow me on that? How many can see that? The far back, I know it's a little small. You okay with that? Okay. Well, what is it gonna be? This isn't showing very well, but how many see this voltage right here is the same thing as this voltage? Let me see your hands. You see it? What's it gonna be? You can get a lot of it. How many know what voltage division is? Can we use voltage division? We sure can. 6 times what? R2 over R2 plus R1 would be that voltage. How many see that? If you don't feel comfortable with that, get the current flowing here. That would be 6 divided by the combination of R1 plus R2. Do you agree with that? Take that current, multiply it by R2. Now you have the voltage across R2, which is the voltage across the capacitor for t less than 0. Do you agree with it? All right, so I'm going to put it right here. So I'm going to say, for this particular case, since there is a voltage for t less than 0, Vc for t less than 0 is equal to, what is it, 6? And R1 and R2 are the same, so it's 6 times 1/2, right? R2 over R1 plus R2 would be 1/2, or it's 3 volts. Do you agree with that? We need to get this one now because it's not 0. Now, the next thing I want to find that K1, but I want to first say, what is the value of Vc as t goes to infinity? I want you to take a look at that and think. When that switch closes, now I'm going to close the switch. I want you to see what happens. Now we have this circuit, don't we, class? T greater than 0, that switch flips at t equals 0, and it goes to the second state. How many see that? Far back there, guys? Can you read my writing? Okay? Now, look, this is out of the circuit. It's only connected at one point. It's not even affecting it. So might as well erase that source and get rid of the distraction. Are you with me, everyone? What's that voltage going to go to on that capacitor and the reason for it? Now, you know. Why? You're right. Is there a voltage or current source in the remaining circuit? Can the capacitor discharge? Yes, right? There's plenty of resistance to discharge. It's got to go to 0. Anytime you have a capacitor or an inductor in a circuit after the switch changes and there's no sources, the final state has 0 energy. In other words, the capacitor has 0 volts. So that means as t goes to infinity, that's 0. I hope this makes sense. That is my K1, right? So K1 is 0. Things are looking up. The more zeros, the better. Now, what's the next thing do we need to get? We don't have to do them in any particular order, but at this point, R Thevenin is probably the best thing to get. Do you agree with that, class? We got the voltage at t equals less than or equal to 0. We got the voltage as t goes to infinity, right? Now we need R Thevenin. This is the one you got to pay attention to this. So what I always do is erase the capacitor at first. That's the element we want the resistance R Thevenin across. And it looks like this. Right? And we want R Thevenin between this terminal and this. We can call it R equivalent. Did you all see the capacitor was there? Tear it out. I want to measure the resistance. Now, some of you still may be challenged by this, but look what is in parallel or series with these terminals. Take a marker. I've done this with a couple people in my office. I think it may be helpful to some. And find a different color marker. I'm going to use black in this case. Go to the other side. Well, I'm not going to use that one at least. And come to the other side. And everything that has black and green between it is in parallel. How many see that? You don't have to do that, but this really just makes it real. You all see this? Because a typical mistake for some reason is they'll say they're in series because they're not looking at the points I care about the resistance across. Do you all follow me? All right. So R Thevenin would be the parallel combination of R1 in parallel with R2. In this case, it's going to be what? 1K in parallel with 1K is going to be
half a K. Do you agree with that, class? How many do? All right, it's 500 ohms or half a K. 1/2 of a K ohm. Now, you can get the time constant tau, R Thevenin, 1/2 a K, and it's times 200 microfarads. That's 200 times 10 to the minus 6. So it's really 0.2 times 10 to the minus third, or you get 0.2 over 2, and that is going to be 0.1 seconds. I'm just putting it down there. It was a 200 microfarad capacitor. Y'all with me? I'm just doing math. Okay with that, class? Now you put the whole thing together in that VC of t. So VC of t is equal to, well, what was K1? Did I erase it? I had it somewhere a second ago. You remember? It's 0, isn't it? Right there. Y'all with me? So who cares? Plus K2. What is K2 going to be? I want you to just take a look at it. We could say if that's 0, just as the switch goes from, you might say less than or equal to 0, goes to 0 plus, it's 3 volts. Do you all see that? How many do? So that means K2 must be 3 volts. If that's 0 and we're evaluating at t equals 0 plus, this is 1, K2 is 3 volts. Then I have e to the minus t over RC, or divided by 0.1. It's really could be e to the minus 10t. Do you agree with that, class? All right. And that's the form of the voltage. Now, question, just take a moment. If you don't understand something yet, you could chat, make sure it's clarified. Do you understand what I did? Okay, if you don't, ask your neighbor or phone a friend. But hear me, don't go yet. I asked for this current. This is usually the step people miss. Look at what is asked for. I got VC of t, that's all I need. No. I asked for this current. How are you going to get it? Anyway. Yeah, you got the voltage, divide by the resistance. Right? You don't always have to take a derivative of VC of t to get the current. You all with me, class? As a matter of fact, that's the last step. I wouldn't do that unless I absolutely had to. I'd look for a voltage difference across the resistor and divide by the resistance to get the current. How many understand this? All right, hear me. I'm going to give you a set of problems that are very basic. The quiz will be based on transient problems related to capacitors that I just outlined. Do the homework. Got that? I'll put the solutions in. And I'll be in my office afterwards if you're interested. You guys understand this lecture? It's hard to tell sometimes.